Now let's turn our attention to the orchestration phase. Remember that orchestration depends upon what kind of parallel architecture we're working with. We'll consider the data parallel model first because it's simplest, then we'll go on to SAS, shared address space, and in the next video we'll take a look at message passing. In the data parallel version, there really isn't much difference between the serial process and that. The only differences here are highlighted in boldface. First of all, note that we have nprox, which is a variable which tells how many processors we have. Another difference is that we've got to allocate a 2D array. That's right here. We've got to read the number of processors and we've got to allocate a 2D array. And we've got to allocate it in global memory. That's the gmalloc statement there. Then there is a mydiff variable, and we'll talk about that in a little while. Then we have the decomp statement that says what topology we want to decompose the grid into. And this one says that we use block partitionings in the x dimension, in other words, row block partitionings. Then we get in the while loop and set mydiff to 0 at the beginning. Our loops are for all loops rather than for loops. That signifies that all iterations of the loop can work at the same time on different processors. So we don't need to worry about serializing the loop. And then when we get done, we have the reduction statement. Reduce mydiff into diff by adding. What that means is that we add all of the mydiffs into a single sum called diff. And that will give us our overall difference between the new and the old values on the grid. And if that difference is less than the tolerance, then we're done. Otherwise, we go back and redo the calculation in the next iteration. The decomp statement both says how to divide up portions of the grid among the processes and how to divide up the data. We divide up the data in the same way we divide up the processes, so that data is located local to the processor that's going to be working on it. We have different options as far as specifying the assignment of iterations to processes. We could do a cyclic partitioning on rows, the x dimension, or a cyclic partitioning on columns. We could do a 2D contiguous block partitioning by using slightly different parameters. The mydiff variable is just to compute local sums over the portion of the grid that a particular processor works on. And then when we get all done, we add those via that reduce statement together to produce the total value of diff, and then that's what we compare to see whether it's less than the tolerance. In the shared address space model, we need mechanisms to create processes and manage them. We didn't have to do that in the data parallel model because remember there's only one stream of instructions and all of the processing elements work on it at the same time. So we didn't have to say anything special to get the parallelism. But in the SAS model, we have one process that starts and then we create our other processes. And as we create the processes, they work in the way that's shown in this diagram. They start out by solving, well, they start out by calling the solve method, and then they go through a number of sweeps. After each sweep, they test convergence and then go back to the start. Now you'll notice that there is a barrier right here, and there is a barrier right down there, which means that no process can start an iteration before all other processes have finished the previous iteration, and no process can go ahead to its next iteration before all the processes are done. There's also a lock here where we test convergence, and that means that we have to add the various sums from the different processes together one by one, because if we tried to add them all at the same time, then we'd have a concurrency problem and we could lose some of the updates. So let's take a closer look now at exactly how the code works. The first thing we see is that both the lock and the barrier are declared. We have the read nproc statement here, just like we did in the data parallel version, and we have a gmalloc statement similar to the one we had before. Then we have to create the other process, and we create them to run the solve method right there, passing a as a parameter. After that, the 0th process also goes ahead, and and executes the solve method, and then it waits for the other processors to finish. In the solve method, the first difference we see is that we have to calculate the minimum row, the first row, and the maximum row, the last row that this particular grid portion works on. And the arithmetic is done in a pretty straightforward fashion. You can easily verify that that's the way to do a block decomposition on rows. Then we get in the loop until the done variable gets set, and we set myDiff equal to 0 because remember those are the diffs that we're going to have to add up to make the global difference. And then we have a barrier, which means that no process can get through until all the other processes have arrived here. Now if you think about it, you want to make sure that all of the diffs are added in the same iteration, and they're all zero, and the total value of diff is zeroed out after that iteration is finished. And that requires some barriers. You probably can figure out exactly why we need barriers the way we do. Just think about it for a few minutes and I think you'll understand it. So then our I loop goes from mymin to mymax. That's the rows that we iterate over. And then we do the for loop. The inner for loop goes across all of the columns, these rows for all of the columns. And then we have the statement that does the update just like we did in the other versions. When we finish, we add the difference between the new and old values of the point into myDiff. After we finish this, we've got to add the myDiff portions into the running diff sum. And in order to do that, we need exclusive access to diff. After that, we wait to make sure all the other processes have gotten here and have added in their diffs before we proceed. Once we do that, we go ahead and test the value of diff to see whether diff divided by the number of processors, n squared, is less than a tolerance. And if it is, we set done equal to 1. Otherwise, we go back and do the beginning of the loop. So then we have another barrier right there. And what that does is it makes sure that all the processors essentially calculate diff at the same time. Or essentially do the test for tolerance. You wouldn't want other processors going ahead and messing with diff before the previous processors got done adding their contribution in. That would really mess up the sum in ways that you can, I think, easily elaborate. So let's take a look at what some of the differences are between the serial program and this. Well, the first process has to actually explicitly create the worker processes, as I said. All processes execute the same code, but unlike the data parallel version, they're not all executing the same instructions at the same time. Then we need the private variables that we've seen, mymin and mymax, to control loop bounds. As we said a minute ago, all processors need to complete an iteration before any process tests for convergence, and they all need to test for convergence before any process starts the next iteration, because if they start the next iteration, then they might mess up the value of myDiff. So that's why we use barrier synchronization. Then of course we've got to put locks around updates to diff, or otherwise we could get inconsistent results. And I think we've already seen this kind of concurrent update here. But if two processes each read a value and then both update it and then they both store it back, the second one to store, this one in this case, wins, and the contribution from the addition in the other one is just lost. That's a race condition. Now one problem with using locks is that we can serialize the whole program. Everybody's got to wait until an update is done. And that's the reason we use myDiff instead of just doing updates to diff, because that way, except for one update at the end of each process, we don't have to worry about synchronizing, because myDiff is a local variable which is just used by our process. And that's one way that our SAS program diminishes the problem of serialization.